Hello to everyone, here we go in another video, and today the topic is unsymmetrical bending. But before to explain an exercise relative to this topic, I want to show you some concepts to derive the formulation of the stress bending due to unsymmetrical bending. So in this case, unsymmetrical bending means that the b vector related to the moment as an inclination with respect, for instance, to y axis of a certain angle. So we have two components of the moment, my and mx, that produce a certain bending on our beam. So you can see here a picture for the notation and sign convention for forces, moments, and displacements. For the unsymmetrical bending, the hypothesis that we make before our studies the same of these made for the symmetrical bending. So all the section remain planar and orthogonal to the longitudinal fiber after the bending stress, and the material is linearly elastic. So means that the material obey to the Hooke law. We have always this stuff, this formula. Sigma z is equal to Young's module times the change in length, that is the strain epsilon z. So we have always this formula also in this topic, also with the unsymmetrical bending. You can see on this picture 60.9 taken from the Megson book. We can see the forces. So P is the lumped force that act on the beam. In this case is the normal force that is acting on this portion of beam. T instead is the torque on that is acting on the beam. My and mx are the two components of the bending moment that in this case is unsymmetrical. That means also that the b vector of the bending moment applied not is acting on only one axis. So after there is a picture that clarify all this. Wy and wx are not the web thickness as explained in the exercise in the last video, but it's related to the distributed load applied in the y or x direction. Instead, the reference here with lower letter V, W, and U are the displacement reference frame and the displacement convention for the positive displacement. So a point of the beam has a positive displacement if follows this direction along the W lowercase. Instead, for instance, a point of a beam has a positive displacement along y axis if follows this direction of v lowercase. Okay, clearly for along the u lowercase letter, along this direction, I mean, we have a positive displacement for all the points located on the x-axis. So this is a simple convention that we use starting from here, but also from the previous lecture that we made. And another important things is this x and y positive quadrant. So all the points that are in this region highlighted in green in x, y positive quadrant, we're going to say that we have a positive moment m if all the fibers situated along this portion that are included if you take a look in the xy positive quadrant are positive bended. That means these fibers are in tension. Also, this fiber have a tensile stress, and mx is positive. So mx is positive if all these fiber here are in tension. Instead, my is positive if all these fiber that we can say all the fiber along the right of the beam if I look the beam from this point of view. So representative of the black arrow. So my is positive is if all these fiber, their projection on the xy positive quadrant are in tension. So these fibers has an tensile stress. What means all these? All these means that mx is positive if is represented in the as in the figure 16.9, and my is positive if is represented by a circular vector, a circular arrow as depicted in this figure. You also note 3 point of view: point of view of y, point of view of x, a point of view of z. So if I see the moment mx from this point of view, mx is clockwise. So mx is positive if I see from point of view of x and clockwise moment. If I look from point of view y, I can see also a clockwise moment. So my is positive if is a clockwise moment. Instead, if I look this moment mz, but this moment is a torque, mz is a torque. For the Italian users, the torque is momento torcente. So also for Italian users, a little bit of translation. Mx e my sono i momenti che agiscono attorno all'asse x, mx chiaramente, e il momento che agisce attorno all'asse y è chiaramente my. Questi sono ovviamente le proiezioni del momento m. So these are the projection of the moment m. Ma il momento mz è il momento che agisce attorno all'asse z e quindi è il momento torcente, chiamato anche torque. If I see from the point of view of z direction, clearly, if I difficult to understand if clockwise or anti-clockwise, I can path. So this is a point of view. From this point of view of the black arrow, I see that this moment is anti-clockwise. So here is the 12 a.m., this is 6 p.m. and so as a clock, no? But if I see this moment from point of view of z, if here from this point of view is anti-clockwise, here is clockwise. So mz is positive if also it is clockwise. So clockwise. So we have 3 moments, mx, my, mz. Mx and y are the projection of this moment of the bending moment applied on the hour beam that is unsymmetrical in this case, and t is the torque, the momento torcente, and all these 3 moments are positive if you make this consideration for my and mx, or if you make a simple consideration from the point of view. From the point of view, you have 3 moments that are clockwise, and so in this case, for convention, these 3 moments are positive. Here, instead, we see an internal force system. Here we have the same beam, this beam, but is cut at a certain station, or station z. Let's say z prime, for example. And we have this, we see from the figure 16.10, we have an external loading system, that is the system seen before, but we have also an internal force system, because if apply an external moment, we have on this phase, clearly if I make a cut, a moment that are in response to the external moment for the equilibrium. But also for the equilibrium, if this is the, let's say, if I see from this point of view, this is the left side of the beam, and this is the right side of the beam. On the left face of the beam, we have a moments and forces that are in opposite to the external moments and forces. You can see my that is opposite to this my. This torque here is opposite to this torque here, that is external torque, and so on. But on the right face of the beam, this face highlighted here, we can see that the my, mx, pt are in the same direction of the external loading system. This is the powerful of this choosing of the internal forces system, because if we take the right side of the beam, so the right face of the beam, this face here, we can apply a same reference system with same convention. So all the moments, internal moments or internal forces, internal torque, following the same convention of the external moment and forces. So clearly, I don't say it before, but mx, my are clearly mx is the moment apply around the x-axis, and y is the moment apply around the y-axis, but is simple to note this clearly. For the other stuff, yy and yx, p, also here we have an example of the lumped load. This is a pz, that is normal, but we could have also a force applied along the y-axis, and so this will be py, or a force applied in x direction will be px. So this is explanation is simple to understand. So the first two things is a simple reference system, and simple is referred simply to the internal force reference system and the external reference system for the convention of the scene. But now we can see more deeply how to resolve an unsymmetrical bending. So we have this picture, the 16.11, that is the resolution of bending moments, and we can see three planes. In each plane is applied a moment, clearly. But in the main plane, that is the plane, this plane that we can name it as pi, as plane pi. In Italian is pi greco, piano pi greco. On this plane is acting the applied unsymmetrical bending moment that is indicated with the letter M, capital M. On the other plane, let's say pi y and pi x, are applied the projections of this moment M. So we have my, mx here on this pi y plane, and my on pi x plane. So it's difficult in first time to note that, but because you can say on the y plane I must have my, and on pi x plane I must have a mx moment. But not here, because if you see this, the black arrow is the moment, the applied moment that we can represented with a black arrow, so as a vector to see how is happening. So if I make a projection of these black arrows in on the y and x plane, we have the so the light blue arrow is the mx projection, and the red arrow is my projection. So because if you see this simple arrow here also in the plane, this circular arrow, you can see this and you can see this. So this is the moment around what axis is the x-axis, so this is mx. This is the moment around what axis is the y-axis, so this is my. This is the explanation, because we have mx in the pi y plane and my in pi x plane. But we have also another consideration to do, is also the point of view where I seeing this moment. The point of view is always in this direction for x, pov y, and pov z. Note that zeta p, the axis of the reference frame xp, yp, zp, zp this is coincident with the axis z of the beam, but the other axis, if you see, have an angle, a certain angle theta, with respect to the previous axis y and x. So we can make this consideration that in this case you are rotating the reference axis of a certain angle theta. So we have to y, from y you pass to yp, and from x you pass to xp. So the inclination of these axis with respect to the previous axis is exactly theta. The point of view of x, if I see the moment m from the point of view of x, I can clearly see that the this moment is clockwise, because if I see from this point of view is anti-clockwise. So if the moment m is clockwise, I can see that also from the point of view of x for mx moment, that is this moment, I can see that the this moment is also clockwise. So mx is a mx for theta minor of 19 degree is positive, so mx is measured than 0. So I can expect that the upper fiber of the beam are in tension. For the my, if I see the point of view of y, here's this, I see point of view of y, clearly the if I make this dashed line, this is more simple to see. I see that the moment is clockwise, because the point of y is also is this. The moment is positive, so we have a this is right, this is left side of the beam if I see from this point of view. So the right side of the beam is in tension, so my is positive for theta minor than 90 degree. But how is the value, numerical value of mx and my? I must calculate these two projections. So mx is equal to, if you see the these arrows, black, light blue, and red arrows, the light blue, as I said before, is the mx. We have also a legend here, mx, my, and m. So mx is equal to m times sine of theta, and my is equal to m times cosine of theta. this is for theta minor than 19 degree. Okay, so mx and my are so calculated. Is the classic projection of a moment m. But when we switch on the theta measured than 90 degree, this other reference frame, we have the orange reference frame y pi, x pi, and z pi. And also we have the black arrow, light blue arrow, and the red arrow. But this consideration that we must do that this quantity here, this angle here is pi over 2. This is 9 degree angle. And this other angle here, I make this draw. This angle here is alpha. Let's say alpha. The inclination of the y-axis or y-plane with respect to the plane where is acting the moment applied m. So in this case we have an angle, a total angle that is theta. Theta is equal to alpha plus pi over 2. So that when I calculate mx moment is m times sine of theta. Theta now is equal to alpha plus pi over 2, but for the associated arcs we can have this quantity sine of alpha plus pi over 2 it's also equal to cosine of alpha. So we have m times cosine of alpha. Yeah, this angle alpha, so we have a projection that is we can also write as m sine theta, but m sine theta is equal m plus times cosine alpha. My is equal to m times cosine of theta, but theta is equal to alpha plus pi over 2, and this quantity is also equal to minus m times cosine alpha. So we have this quantity that is positive because cosine of an angle is also a positive function. Not cosine of alpha, but is sine of alpha here. Here, for the my moment, we have a moment that is negative. So for a certain angle alpha, we have a negative moment. And you can see also here, because we have mx that is acting in this way. If I see from this point of view of xp as a moment, is a clockwise moment, and also this is mx induce a tension bending on the upper fiber. But my, if I see from point of view of y pi, we have an my that are acting in this case, in this direction y. So the left side of the beam, the left fibers of the beam are in tension. That is opposite in the consideration that we made a few moments ago. My is negative and mx is positive for theta measured than 99 degree. So we can see an exercise that explain this, but after this video. In the last part of this video, we make some considerations to determine the natural axis position. So we have in these two pictures are in a one, and here we have a zoom of this picture. We can say that we have an unsymmetrical bending moment. So clearly, as said a few seconds ago, we have an my and mx moment that we can see here. So and also here. But this thing is clear at this level. Now, how can I determine the neutral axis position, and how can I determine this angle? Because the neutral axis in this case is not coincident with the x-axis as said for the symmetrical bending and as seen from the exercise of a symmetrical bending. If you see this picture here, the B picture, the zoom of the B picture, we see a point P, this point P, where we take a small portion of area indicated with delta A. In this point P, we take this infinitesimal portion of the area indicated with delta A, and point P is individuated from the coordinates x and y. So also this infinitesimal portion of area delta A is individuated from the same coordinates of the point P. The neutral axis NA has an angle with respect to the x-axis, that is this angle alpha, this angle here, in clockwise direction. So as made for the symmetrical bending, where we say that we have a change in length epsilon z, the strain is equal to change in length divided by the initial length, so that is the delta L divided by L initial. So we have obtained from the previous lectures that epsilon z is equal to y divided by the radius r. In this case, we make a same consideration where we have a radius r that we indicated now with the letter rho, the Greek letter rho, and the y, and y is the distance now from the delta A from the neutral axis. So y is zeta, this other Greek letter. So if make a similar consideration, we can say that strain epsilon z is equal to zeta divided by rho. This is this is first equation, second equation. This is similar to the equation obtained from the previous lecture of the symmetrical bending. Symmetrical bending is this equation here. Now we can also express the strain sigma z, because as I said in the first part of this video, the material is linearly elastic, so obey to the Hooke law. So sigma z is equal to Young's module times epsilon z. So this is a simple equation. Third equation. Since to here is all is same to the discussion made for the bending, symmetrical bending. But let's go to see other stuff. We can say also that the first moment of the area is equal to 0. The first moment of area in Italian is momento statico, because here we no have a axial force applied to the beam. So we have that the integral on the whole area of the cross section of sigma z times dA is equal to 0. That we can write also as sigma z is this quantity, E times Young's module times zeta divided by rho dA is equal to 0. Young's module and the radius rho are are constant quantity. We can extract them from the integral sign, so we have a divided rho of the integral of on the whole cross section of the zeta times dA is equal to 0. That means that the integral on the whole area of the cross section of zeta times dA is equal to 0. So this is the proof of that the first moment of the area of the cross section is equal to 0, so il momento statico è uguale a 0. What means that this equation here, what tell us this equation here? The third equation, all this equation tell us that the neutral axis pass through the centroid of the cross section. Clearly you can see here, this is the centroid of cross section. This fact here, this stuff here, this formula here, tell us that the if the momento statico and first moment of area of the cross section is equal to 0, the natural axis clearly sure pass through to the centroid of the cross section. Now, also from this picture here, we can express the distance zeta as a function of x coordinate, y coordinate, and mostly of the angle alpha. So how can derive this relation? If I take this axis, so the neutral axis, and take another axis that is parallel to the neutral axis, that is this axis here, we made with the green pen, this quantity here is also y, so is also the distance from the delta A infinitesimal area to the x-axis is y. So, but this is a right triangle where I can apply the well-known formulas of the right triangle, but we must derive the angle of this right triangle. So this angle here and this angle here is 19 degrees, this angle in light blue. But we can note that this is alpha angle because the green axis is a simple this axis that has been displaced from the neutral axis to this point here, for example, this point highlighted here. So the inclination of this green axis with respect to the x-axis also is also the alpha angle. So also this angle here is alpha angle. So this angle here highlighted here. But the angle drawn with the light blue pen is 19 degrees. So we can have that this angle here that in magenta, that is drawn in magenta, for example theta, but notice the theta of the shown in this picture here. Notice this angle, but an angle taken for this explanation. Theta is equal to 90 degrees minus alpha. So minus alpha. So this other angle here, clearly this angle here highlighted in green is 90 degrees. So if I want to obtain this angle written in blue with the blue pen, let's call it gamma. Gamma is equal to clearly pi minus what? Minus theta plus pi over 2, but this quantity is equal clearly to pi minus pi over 2 minus alpha plus pi over 2. And if you make some calculus, we obtain that gamma angle is equal to the alpha angle. So gamma is alpha, is equal to alpha. So I can express this quantity here that I call as zeta y. So we stay here, for example, zeta y zeta y, zeta y is equal to y times cosine of alpha. Now we must determine zeta x. Zeta x, if you note this quantity here, this is also x. So is x coordinate. Clearly, if you understand this game, this is the zeta x portion, and so the right triangle that we take in account now is this triangle here, where this quantity highlighted with the orange pen is pi over 2. So this quantity is also zeta x, that is also this quantity here, this and this here. The angle is alpha, so we can obtain that zeta x is equal to x, that is this quantity here is also this quantity here, so is x times sine of alpha. So we obtain that zeta is the sum of two quantities, zeta x plus zeta y, that is equal to x times sine alpha plus y times cosine alpha, and this is zeta. So we obtain this formulation here for zeta, that let's say the fifth formula. Now we can express the sigma z is equal to Young's module times zeta divided by rho, that is epsilon zeta, all this quantity, but this is equal to Young's module divided by rho multiply for x sine of x plus y cosine of x of alpha. So x sine of alpha plus y cosine of alpha. Sorry for that. All the stuff here is the sixth equation. Now, all the moment applied in this example are positive. So if you take a look to this also consideration, this equation, you see that the mx is positive and my is positive. We have that the mx is also equal to the integral on the whole area of the cross section of sigma z times x, that is this quantity here, x, this quantity here, that is the arm of all the force applied, let's say in y direction in this case, times the a, and my is also equal to the integral on the whole of area of the cross section of sigma z times the arm y in this case times the a. So from here we can say that this integral must be positive. This integral is clearly positive because mx and my must be positive. So this quantity is measured than 0 and this quantity is measured than 0. So this is the equation number 7. And now we can express the mx and my moment. So if you make some calculus, you obtain this stuff. So if you make some calculus, substitution of the sigma z here, sigma z expressed as this quantity in the sixth equation, you obtain clearly this formulation, this equation for mx and my. This is the formula number 8. We obtain some things that are known at our case, that are this quantity here, this and this one. All these integrals are simply the moment of inertia with respect the y, the x-axis. So this is ixx, moment of inertia with respect to x-axis. This is the moment of inertia with respect to y-axis, so is iyy, and the integral of x times y times dA, so this integral here is the product of the inertia ixy. So the other quantity, so Young's module divided by the radius rho and sine alpha and then cosine alpha, are all constant quantities. So this quantity we can extract from the integral C. So we have that the mx we can express as with the matrix notation, that we have Young's module divided by rho, matrix of the moment and product of inertia. This is not the tensor of inertia tensor, so I write here yy. So we have this is a constant, so is Young's module divided by rho, product of inertia ixy, then ixx, iyy, ixy, multiply for the vector, multiplied for the column vector sin alpha and cosine alpha. All this is equal to the column vector mx and my. This is in matrix notation. So if you note here, if I expand this formulation, I obtain Young's module divided by rho sine alpha times x plus E divided by rho cosine alpha times y. X and y I know because clearly someone give me the coordinate x and y of the point P and of the infinitesimal area delta A, but A divided rho times sin alpha and A divided by rho cosine alpha, what is the value of these quantities? I don't know. I mean, I must calculate this quantity, and I calculate this quantity from this notation here, from this matrix notation. So is the ninth formula. I can obtain the E rho multiplied for column vector sine alpha cosine alpha, that is equal to the inverse of the matrix, let's say I matrix, inverse of this matrix here. This is the I matrix for me, not is the identical matrix. So multiply for the column vector, let's say moment column vector xy, to remember us that in this vector there are the projection of the applied moment, and that is mx and my. So I must invert this matrix. Clearly the procedure is quite long, but is simple for you to invert a 2 times 2 matrix as this. If you invert this matrix, you first of all must calculate the determinant of this matrix, and clearly this determinant must be not equal to 0, but major or minor than 0. The depth of matrix I clearly is equal to the product on the first diagonal, the main diagonal of the matrix, that is this diagonal here, and we have ixy at square minus the product on the secondary diagonal of the matrix, that is equal to ixx times iyy. So when you make the inversion of the matrix y, you can highlight it the minus sign, so I can write the depth of I as minus of ixx times Iyy, and this is minus Ixy at score, because when I made the inversion of this matrix, I've obtained I at -1 of this minus, this is the that obtained here is minus Ixx Iyy minus Ixy at square, multiplied for highlighted another sign mine from the transpose of the algebraic cofactor matrix. So we obtain a matrix like this. To invert this matrix, I can first of all calculate the determinant of the matrix I. So calculate the algebraic cofactor of this matrix and transpose the matrix of algebraic cofactor. I highlighted another minus sign that derives from the transpose of the cofactor, algebraic cofactor. So I can simplify these two minus sign to obtain the formulation of. So when we obtain these, we can return here in the formulation number 10. In the formulation number 10, substitute this quantity here, the inverse of the matrix I, and we can reach this result for A Young's modulus divided by radius R times sin alpha, and E divided by rho times cosine alpha. We obtain this. So we obtain this 11th formula. So E Young's module divided by rho times sin alpha, and Young's module divided by rho times cosine alpha is equal to this formulation that we see on the screen. Clearly is obtained from this equation number 10. So number 10 gives us the equation number 11. If now I put this equation, so this value of E Young's module, so these results of the 11th formulas here, just here in the 6th formulation. So this proof is a little bit complicated, but not impossible. It's complicated because you must go from the formula to the another formula and return to the previous formula. So if I put the 11th results in this 6th formula, I can obtain the relation for the sigma z. That is the relation that we want to reach in this lecture. So we obtain finally that sigma z due to unsymmetrical bending can express by this formulation. This is the formula. The 12th formula is the formula to calculate the stress bending due to an unsymmetrical bending. So is quite long with respect to the previous formula of the symmetric bending, but if you note, you can obtain the same formula for bending for symmetric bending, making what consideration? Making the consideration that my, for example, I say that the moment is applied only on the vertical plane. If it's applied only on the vertical plane, you must know that in the vertical plane is acting mx. Vertical plane is this. Vertical plane is this. So if the only moment applied is in the vertical plane, so we have a symmetrical bending moment where mx is not 0 and my is equal to 0. So if I put this quantity here, everywhere the my is we can see my. Now my here is 0 and here is 0. Clearly, if I have a symmetric bending moment, I have only one direction where I must calculate sigma z, and is the y direction on the vertical plane. So also x is equal to 0. So another consideration to do is x is equal to 0. We have a simple point 0 y. Okay, so all these quantity, all the first quantity here is identically equal to 0. We obtain also this quantity. We obtain that sigma z is equal to 1 xx y minus xy x squared plus times mx iyy times y. So, but now this is the equation of the bending stress of a symmetrical bending applied along vertical axis. But for obtain the same formula studied in the first video, in the second video made in this playlist, I must make another consideration that if the cross section is 2 times symmetrical, because if this section is 2 times symmetrical, I means if the section is symmetrical also with respect symmetrical with respect to the x-axis and with respect to the y-axis. If I can prove this, if y and x-axis are also two symmetrical axes, we obtain that this quantity identically equal to 0. So we obtain that the sigma z in this case is equal to mx iyy divided by axx iyy times y. But I can simplify this quantity here and obtain that sigma z is equal mx times y divided by axx. This is the formula, 12a formula, the formula that we obtained in the second video of this playlist, and this is for symmetrical bending moment, sim bending moment, 2 times sim cross section, and clearly with moment applied in the vertical plane for the instance in this case. So if we have all these three hypotheses verified, we can apply this formula. That is the same formula of the also of the e-beam exercise made in this playlist, because in that exercise we had a symmetrical bending, a 2 times symmetrical cross section, and a bending applied in the vertical plane as a symmetrical bending moment. So this video is quite long, so now I can stop this video here. For the exercise, we make the exercise in the next video, but you can derive this formulation follows this video. I hope that is useful for you. And let's see if I forgot something. I think no, but clearly you can here derive all the other consideration about of your cross section. I can highlight this, that 12 formula is the general formula. So this formula here, the 12a formula, is a derived formula of the 12 formula. Okay, so this is a particular formula because we have these three hypotheses verified. But the general formula of the bending stress is this. Okay, this formula is applied at generical cross section. Then this cross section is 2 times symmetrical, that we have a symmetrical bending and so on. We can simplify this formulation to obtain a more compact formula, but the general formula is this. So we will see in next video. Bye.